So this is much more easier way to find it, because you don't need to solve. If we really want to find this, okay, or this is the way you should find the technical V function and let t goes infinity. So first of all, you have to solve it. The second way is that even though we know Vjj easily, but we should find the mu Jj. This is another way, right? Find the Jj here. Okay. And of course, that the other is this one. Then the third one, right? We have three. You see, the first one to find the limiting probability is just by computing the transient probability function first. And once you know this one, okay, you can find the Pj. And it's possible that because that with this formula you can consider non-ergodic continuous time multiplication, because that the Pj can be zero, right? So you can find it. So no matter the continuous function is ergodic or not, you can always find the Pj. If you are, because up to now here we are talking about irreducible, right continuous, conservative regular Markov chain. Okay, and so that by the theory of semi-Markov processes, that this probability must exist. Alright, and so and in the theory, the same theory that this value is equal to the ratio here. Okay. Alright, but to use the ratio, you have to find the mu Jj. That is another problem, right? You have to find it. Yeah. So the other way is that we can, if we have more information, says that the invariant Markov chain is not only irreducible but also positive recurrent, then we know this invariant Markov chain has a stationary distribution, so we can solve the stationary distribution first. Right? When we solve them, then we can find the Pj here. Right? Before we use this one, we have to solve and check, right? So and then you have to check whether this series sum is infinite or finite. If it's finite, you have to find its value. Okay? Its value, the series sum. So you can see, even if this formula is still a lot of computation to do, right? A lot of computation. And but up to now, you can still consider non-ergodic very continuous conservative regular Markov chain. Okay? Up to now. But if we know that it's ergodic, then we can solve it directly. Okay? So we can solve it directly. But another way, if we don't know if the right continuous conservative regular Markov chain is ergodic or not, right? Then we just go ahead to solve this linear system. And we find that there is no solution. Because the O0 solution must be the homogeneous, because it's a homogeneous system. So zeros, Pj equal to 0, OP equal to 0 is the solution. Right? So if you find that the only solution is O0 to satisfy O0, no solution is satisfy this one, then you will for sure that this right continuous conservative regular Markov chain it's not organic. Because if it is organic, you must find a solution. This is from theory, okay? So you must find a solution, means that Pj greater than 0 and the summation of Pj is 1. So if you cannot find, you make sure that you cannot find any solution subject to these conditions, then this continuous conservative regular market chain should be non-organic. And all the limiting probability Pj are 0. So that's fine, right? We just go ahead to try to solve this homogeneous system of linear equations. Yes?
Why IJ equals to the sum of QIJ?
Because pi j is the stational, we assume pi j is a stationary distribution for reducible and positive recurrent. Okay. And it should be unique, right? From our study of discrete time Markov chain, any reducible positive recurrent discrete time Markov chain has a unique stationary distribution. Okay. And it is satisfied because it's stationary, so it satisfies this linear system. Other questions? All right. So the equation here, this one, is called the balanced equation. Very famous equation. All right. And so you can see the interpretation. What is Pj? Pj is the probability. So because that it is organic, so we may assume that the Markov chain has initial state, which is just this stationary distribution. So Pj is what? Is the probability that the Markov chain is in the state J, the probability. Right, so this is the probability in the state J. And what is Vj? Vj is the rate, right? Is the rate for the Markov chain to flow out of J. Alright, so this is the non-round transition rate at which the process leaves stage, right? Leaves stage. Now what is this one? So this is leaving. And because that you should balance, because that is organic, right? So the behavior. So you have the chance to leave stage. Now you must have the chance to get into J, right? So the probability should flow back to J. So and what is the probability flow back to J? It should be back from the state other than the J, right? So it's from I. And from I, and this is the probability that the Markov chain will be stayed in state I. And what is this? This is just the probability. The rate of probability flow from state I to state back to J. Okay, so that is the situation. Okay, and we know that the QJJ is 0. Okay, QJJ is 0. Because it's free I, it's so let's see. Right, so I have to. So you have only when I don't equal to J, you have the transitions. so the balance is you balance the transition, right? Okay, you balance the transition. Okay, so we actually we complete the theory of the niggling behavior of the Garden, especially the Garden continuous time markup. Right. So we will consider a special type of very continuous conservative regular markup chain. The first type called first stage process. So a first and stage process, okay, is a special type of direct continuous conservative regular markup chain. And the state space still is countable infinity, so it consists of all the integers greater than or equal to 0. And very interesting is that the rate of probability flowing from I to j will be 0 if the distance between these two states is greater than 1. Okay. So the thing is that so it's just like 0, 1. So we can express the state as a linear chain here. And we have a probability flow from state I to state I plus 1. Right? So from I to I plus 1. So the Qi I plus 1 usually non-zero, and we call it as number. So it's here. So we have Q 0, 1, Q 1, 2, Q 3, and Q 3, 4, etc. So we have, and because that this is the rate of probability from I to I plus 1, so we call it as the first rate, because that with this rate, the state of the Markov chain increase. So we call it, so we define it to be number 0. Okay. So this is the first rate for state 0, first state 1. And another transition rate is that from a state I to state I minus 1. Okay. So you have this rate. So you have Q1, 0, Q1, Q2, Q4, 3, so this is Q1, 4, etc. And because that this is the rate of probability from a state I to a state lower state I, is I minus 1. So we call it base. The base rate. Right. So it's mu 1. Okay, so the mu 1 here is called the base rate. And this is mu 2, mu 3. 4 and V5. So it's called the base rate, this is the first rate. Okay. With this name, then such a very continuous conservative regular Markov chain would be the first and third stage process. Okay. And remember that it is a conservative Markov chain, right? So we know that the balance is Vi, which is equal to summation of the Q and J, J not equal to I. Right? So we have this identity, because it's conserved. Okay, so this is conserved. And so from this equation, we know that the mu is 0. So here, right? So here we mu 0 is equal to lambda 0. Okay, first rate, and 1. Okay, it's mu 1 and lambda 1. Okay, lambda 1, because Vi is the total rate of probability from leaving state I, right? And so because of conservative property, that is going out, so it should be flowing to state 2 or ground state 0. Because this is the only way, because of this constraint, and we can only flow from state 1 to state 2 or from state 1 to state 0. So this is mu 1 and lambda 1. And for state 2, mu2 is equal to mu2 plus number 2, etc. Okay? Okay, so with the first rate and the base rate, we can find all the mu. Okay? We find all the mu. And of course, we assume it is regular. So from the regularity, you can see that right. So the regularity is here. That is satisfied. So the mu function here should be infinite. So you can see that the rate, all this rate cannot go smaller and smaller, right? Because if it's too smaller, then this summation may be converged to a finite. So, but we insist our first stage process to be regular. The regularity means that the first explosion time will be infinite, which will be 1, right? Because if the first explosion time is finite with positive probability, then the Markov chain will stop at a finite. Okay? And that is not we want to stop. So, so remember, every time when we talk about the first and stage process, we are talking about regular Markov chain, conservative and regular Markov chain. And here we use the conservativity, right, to compute the total rate of probability flowing out of state I by using the burst rate and the base rate. Okay. All right. So so we know that. So if a good picture is to do it this way. So there's no rate flow from, for example, from state 0 directly to state 2. No. impossible because that here, because the distance 0 and 2 is greater than 1. Okay, so there is no such state transitions possible. Okay, it's impossible. That. All right, now the embedded discrete Markov chain now has one state transition probability like this one. Okay, so the Q I to I plus 1 is lambda I. The lambda I is the Q I to this is Q I to I plus 1. But this is exactly the first rate lambda. And the denominator, of course, is VI. Okay, I think it's VI here. And so, okay, and so for all I greater than 0, and for all I greater than 1, because the U go up. So this is the base rate. Okay. And the sum. Oh, we already know that mu I is lambda I plus 1. And of course, if I equal to 0, there is no base rate, right? So we assume that the mu 0 is 0. Okay, we assume just by assumption, okay, to have the formula to be consistent. Okay, so a very prominent examples of first and best process include like MMS, queuing system, and Poisson processes. Because Poisson process, basically Poisson process is only just the first process because there is no test. Okay, so Poisson process is a very special kind of first and test process because it is just a pure first process, no test. Because you're counting, right? You count. So the state, the number, each time you have a arrival event, you count the number up one, right? So Poisson process is a pure first process. So now let's see what is an MMSQ system. Alright. So the first M means that it's Poisson arrival with rate lambda. So Poisson arrival. So the input of the Q is a Poisson arrival. The second M means that the server in the queue you should have a server. The server is the customer. So we assume that the server has exponential service sum with the rate mu. This is the rate mu here. And the little s is the number of servers in the queue system, queuing system. And so S of t is the number of customers in this queue. Okay. So in this queue, including the customer being served, right? And we will show that S of t is a semi-Markov process with exponential transition times, and the exponential transition time depends on the entering state, right, of transition period. Okay, so let's see. Suppose that at time t, the number of customers in the queue is n, right? So we fix the time, and the number of customers. So then, this is the queue, okay, and the service desk here. Right? So it's server 1 and 2 up to S here. And the customer will come. Okay. And the queue here, the queue is non-empty, means that they are customer here. So if the queue for example people waiting in the queue because all the servers has been occupied. Okay, so this is the queue, and so the queue is empty if that we have enough server to service the customer at that time. So you can think about that. At the time t, the total number of customers in the queuing system is n. So including here or here. Okay. And if a customer complete, so the arrival process here, the arrival process is a sum. Okay. So the interval time for the customer will be exponentially distributed with the parameter number. And each customer will be served by a server, and the time spent for the service is also exponential, and is parameter mean. So after the exponential distributed time, the customer will leave this system because the service is complete. All right. So now when n is 0, when if n 0 means that at some time the system is empty, no one is in service, no one in the queue. So no customer are either in service or in the queue. Right? So only the some input process influence the queue system because now the system is waiting for the next arrival, and because at this time moment because the interval time is exponentially distributed, and we know exponentially distributed random variable is memory release. Okay, so at that time when there is no arrival, then how long do we need to wait for? Well, the same. It's just the exponentially distributed random variable because it will forget the past. Alright. So that so we are waiting for the next customer, and the waiting time should be exponentially distributed with the parameter number. Right? So this is what. So the duration for the next arrival is exponentially distributed with the parameter number. Okay? Alright. So this is called number 0. That means that from 0 to 1. Right? Because the system, if there is 1, so the first row, the 1 is always, we call the number 0 is non-adaptive. Now, if the number of customers in the system is between 1 and s, so it's less than or equal to s, means that we have s servers here. So everybody gets served. Right? This moment. So there are n customers in service with exponential service time. And because every service time is memory use, so the remaining service time for customer I to complete the service remain exponentially distributed with parameter number, the mean. Okay? And so now the waiting time, the remaining time for the n customer will be W1, W2, and Wn, and we find the minimum because we want to learn how long should we wait for the first customer to complete its service. Okay, and so we have to find the minimum. All right, we call this minimum as W. So W is the remaining time that a customer will complete the service and leave the system. When it leaves the system, then for example, if we now the system has 3 customers here, and if there is 1 customer complete the service, then the state will reduce to 2. Okay, so this would be the test rate for state n. Okay? And so now we complete. So we should find the distribution of this random value W. Alright, and so we use the tail distribution. Okay. We compute the tail probability here. So the minimum is greater than t means that everyone is greater than t. And because that the service behavior, they are all independent, so it comes to this one. Okay? And so that this tail probability is exponential function here. So come up that the W is exponential distributed, and so the rate would be m mu. Okay? So the base rate would be m mu here. Okay, so the parameter is mu1 is mu. But at the same time, some rubber process will input a customer, okay, in time mu, which is exponentially distributed with parameter lambda. So lambda n is still lambda. But at that time, the input process, the input potential is still supply a customer with direct lambda. Okay, right. So so the burst rate is still lambda here. So the holding time of state n from time t is the minimum. Okay, is the minimum. This is the holding time, because either a customer will complete the service and leave the system, or there is one more customer comes in. And a customer comes in, will say, okay, in here we model to be the random variable v, and which is exponentially distributed with random number, right? So that the minimum, because W is the time to wait for the first customer to complete service, and we know that the W is exponentially distributed, right? Exponentially distributed with the parameter mu(n), which is n times mu. And the V is the input process to give us a new customer, and it's also exponentially distributed with parameter lambda. Okay, so the minimum, again, the minimum actually from our previous computation, the minimum. So if we take the minimum of exponentially distributed independent random variable, then it is also exponentially distributed. And its parameter is just the sum of the parameter of each exponentially distributed random variable. Alright, as we compute here. So the minimum, because W is exponentially distributed parameter mu(n), which is n times mu. V is also exponentially distributed with parameter lambda. So the minimum, again, is exponentially distributed. And the parameter is the sum of the parameter of W and the parameter of V. So that this is m mu plus time. And the holding time, and so the rate would be mu(n). So mu(n) is just the exponential time, okay, with the rate. So mu(n) is this is sum. Okay. So that this is the situation, because actually I forgot to mention the MMSQ in the textbook. Right? The textbook have shown that the MMSQ is a continuous time Markov chain. That's why. So we just need to develop the rate of probability flowing from state I to state j, or the rate of probability flowing out of the state I. Means that we just need to find the Qij, okay, and the V1. So we know that this is the situation for n between 1 and s. Okay. Now, if n is greater than s, means that with the Q is now non-empty. So somebody will be in the system. But if n greater than x, then the s servers are all occupied. Right? So that the mu1, so the test rate will be with S mu, because this is the maximum test rate we can have. And the first rate is still lambda, again, because of some process. Okay, so this is the first rate. And so the mu1 in this situation will be S mu plus lambda. Right? So it becomes constant if n is greater than s. So that the birth rate is constant, the test rate is constant, birth rate constant, and the mu n is also constant. So we conclude that the number of customers in NMSQ system is the birth and the test process. Okay? And with constant birth rate here, and the test rate is here. Okay, so now consider an irreducible birth and test process. Right. We consider it is irreducible, but we don't know whether it is the Guardian or not. Right? So we are going to solve the balance equation. But because, so we are going to solve the balance equation. As I mentioned, right? Because up to now we don't know whether it is a Guardian or not. So we try to solve the balance equation. Right? And then you can see the balance because of the birth and test process is so special. So that the balance equation takes the special form. Right? And so we write the above equations. So we move the right hand side to the left hand side. Right? And for here, we actually just move the mu I and the mu j and pj to the right. But we move the mu j and pj part over here. So you can see that the right and the left has the structure that when connect with this one, you will see that the difference, all the difference will be equal to 0. Okay, so you can see when you by recursion that j go to j minus 1 and go to j minus 2 and then go to j equal to 0. So they and go to 0. So we show that lambda j pj is equal to mu j plus 1 pj plus 1. And this is the I think this is very intuitively true, because what is pj? pj, for example, j is equal to, right? So pj is the probability that the state, the first stage process will be in the state j. So it's this one. And lambda j is the birth rate. So it's the rate of probability flow to stage, right? And so because it's balanced, so the stage rate should have a rate of probability flow back to 2. So this is the PJI, and this is the pinch rate. Okay. So this should balance here, right? So we look at this part, right? The only way the probability flow is from here 2 to 3, and the only way for the probability flow back to the left hand side is from 3 to 2. And because that we are now in the steady state, so the probability flow should balance here. Okay, so this is quite intuitive. Okay, next time here when you dissect the Markov chain into 2 parts, then the flow should be balanced. So we have these equations. So with these equations, now Pj plus 1 can be computed from Pj, right? And the weighting is lambda j divided by mu j plus 1. So now, so recursively, we can to the replacement 1 by 1. And finally, any pj plus 1 can be expressed as a constant times p0. Okay, so given the p0, we can find the pj plus 1 because we know the birth rate and we know the death rate. All right, so now go to solve it. So now we apply the summation, it should be equal to 1. Right? And so that the sum is from that, the p0 becomes to the inverse of this summation. This is p0. Okay? And the pj will be this one. Right? So now, so this irreducible percentage process is a guarded if only this sum is found. Because if this sum is infinite, then the pj will be always 0. Okay? Always 0. And so the irreducible percentage process becomes non-guarded. Alright, and this summation can be infinite or finite. Depends on the birth rate and death rate. Okay? You can make an example. Some examples make that this summation is finite. Some examples make this as infinite. Okay, so basically we solve the asymptotic behavior of the first and death process. Alright, so now some detailed analysis. We know we analyze the MMSQ in system to be birth and death process. But how do we identify a continuous time stochastic process with state space n0 to be a birth and death process? How come? Okay, how do we know it? Before we can guess that this process is the birth and death process. Alright, so a way is to analyze these sample functions or this sample realization. So now, a sample function of a birth and death process must be a right continuous state function, right? With only given form. So the state function means that it should be when each epoch for state transition, it can only go up 1 unit, right, or go down 1 unit. So up and down for only 1 unit. Okay. And without any finite first explosion time because of the regularity, right? So if there is a finite first exploration time with positive probability, then of course it is not a birth and death process because it's not a regular process. Okay. So first of all, we observe the sample functions. Okay, the sample functions just like here. Okay, so suppose that the state is from 0 beginning, initial state is 0, then it can go up 1 unit, and then down 1 unit, up 1 unit, 1 unit. You cannot, if you observe a sample function that from 0 and up 2 units, then it is not a birth and death process. Okay, so this is to identify the first one. Then, secondly, the state at the transition epoch must form a discrete Markov chain, right? So you should study the embedded Markov. The state, embedded state at the transition epoch. So you have to sample and then justify that the Yn is a discrete Markov chain. Thirdly, at the transition epoch Sn with state I, the holding time, okay, of state I has to be exponentially distributed. So you should just justify that the holding time should be exponentially distributed with a parameter mu I, depending only on the state. Okay? And independent of all others, including n and the next state. This is from the property of semi-Markov processes. So that you should study the holding time, and to make sure the holding time has exponentially distributed, and the parameter is mu I. And this mu I depends only on the state. So that's it. This is the good things for you to justify whether a continuous time stochastic process be occurs in this process. Of course, you have to justify more things like because from here you know you can only have a birth and death. Any questions about birth and death processes? Because in the history of stochastic processes, the birth and death processes, the class of important stochastic processes to be investigated in history. Okay, so now we look at homomorphic differential equations. Because we talk about a lot about limiting probabilities, especially the limiting probability of ergodic continuous time Markov chain. Because in these cases that the limiting distribution can be computed without going to solve the transient probability function. Because to find the function itself, sometimes it takes a lot of effort. But this section gives us a tool through differential equations. So that we can solve the transient probability function from a system of differential equations developed by Kolmogorov. Alright, so the question is, how can we obtain the transient probability functions explicitly? Okay, when the infinitesimal transient rate are given. So when we are given the VY, the QIJ. Okay. And we will see that we will find two sets of differential equations. Alright. For the same purpose. For the same purpose. But they have quite different mathematical properties. Alright. So the first theorem is called Kolmogorov's backward equation. Now, so for a continuous time Markov chain with conservative transient probability functions, okay. Then for conservative, then we have these differential equations. Right? So it demands that the transient probability function Pijt has a derivative at each time. Okay. Not only at the right hand. Of course, if t is equal to 0, this derivative means the right hand derivative. Okay? But it implies that if we have conservative transient probability functions, then that it has derivative all the time. And this derivative is equal to this summation. And I will explain why it's called the backward equation. Okay? And then the system of, so it's first order, right? Because it's the first order differential equations, and it's a system, so we can make it as a metric form, right? So the PT is a matrix. Okay, it's a matrix, and the components are state changing probability functions from state I to state J. Alright, and the R is just the infinitesimal rate we have. So it's here together. And those sum equal to 0. Why? Because that V0 is the rate of probability flow out of state 0. And the Q is the rate of probability flow from state 0 to state 1. From 0 to state 2. So they will go out. And by the conservative property, the sum Q0, 1, 2, 0, 2, etc., the sum of all the Q is equal to V0. So when you put minus V0 here, the low sum should be 0. Okay? So the R matrix consists of the infinitesimal, the rate. So it's actually the change, is the rate of change, okay, of probability. Alright? So this is matrix and times the changing probability matrix again. PT. So the whole system becomes to this system. Okay? So it's much more simple, right, to look at the compare with this 1.12, right? Yeah. So actually you have that. Alright, so let's how to prove it. Divide, so we're dividing the difference by h out by minus h respectively, and taking the h goes to 0. So we write so this is, what is this? This is the right derivative. This is the left derivative, right? And of course here we let t to be greater than 0. Because when we have a conservative, we are considering standard one, right? And so the right derivative exists at t equals to 0. So we look at the right derivative and the left derivative. Okay. And so by the Chapman-Kolmogorov equation, we can split. Alright. So the Pij from, we take t plus h time unit to go from state I to state j. Then we can decompose this changing probability to be, alright, you go from I to, you take the h unit of time to go from I to k. And then you take the t unit of time to go from k to j. And for all the k not equal to I, and the other term is for k equal to I, right? So the other term is here. So we have Pii and Pij. And so in this term we absorb this term here. Alright? We absorb this term here. So this is minus 1 here. 1 Pij is this term. Okay. So now the ratio comes to two terms. The one, this is ratio. Actually, it's a series sum. And similarly, for this one, we again take the by expanding Pijt. Okay. So Pijt is that we go from I to k in h and from k to j in t minus h. So we expand this term by the Chapman-Kolmogorov equation. Okay, by Chapman-Kolmogorov. So we have a minus h here. Okay, because minus h minus 0. So now we cancel the minus sign here, so we have a positive h. And the rest of the term is that when k equal to 1, equal to I, and so we have this term. So this is for all the t greater than 0 because this is the right derivative. So we can allow t to be 0. But for here, for the left derivative, we should put at t greater than 0. And for all the h less than or equal to t. So now by the continuity of Pij, okay, and the existence of the right-hand derivative at t equals 0 in the theorem, so we have that the term here, this, right? This is just the right-hand derivative. So this is go to the Bi and P and T. So we have that term here. Okay. So for both cases, here with 1. So we have the limit, and this also has limit as h goes to 0 by continuity of Pij. So this one will go to Pij, okay, by the continuity, and this limit of the ratio goes to the rector to Bi. And to show the existence of the limit, okay, this one for the right derivative and this one to replace this function by p aj t minus h for the left derivative. So we first note that we can compute the lim, right? Here. Alright, and so the lim, it has a low bound as we check the n. So we just, because this is in general this is a series sum, because you include many terms here. But we can use a low bound, okay? So by taking only the finite number of terms here. And so because the ratio has a limit, it's limited by theorem, 1.5 or 0.1.2 and 5.1.3. But this is QI. Okay? So we have, so because this is finite sum, so the limit can move into here, and so we have that. Okay, so we have this. And then by letting n goes, because this is true for all the capital N, so by letting n goes to infinity, okay, then the lim has this low bound. Now we consider in soup, and we want to find the limiting supremum, and so we will decompose it into two terms. This one and this one. And this one, why is an upper bound? Because that we replace when k greater than equal to n, we replace this tangent probability requirement by 1. Because this is probability, so any probability has an upper bound which is 1, right? So that this is, of course, this is an upper bound. Right? So we have an upper bound here. And now, again, where is the, let me see. Oh, okay. Okay. Let's see. Okay. Let's see here. Summation P I K H K. So this is equal to 1 minus summation K less than n and P I K H. That's okay, because the summation for all from P I K, the transition P I K equal to 1. Okay, because you can transit to any state K, so the summation should be 1. Alright, and so you have that. Now, we assume that I, okay, is less than n, because we can pick n big enough, right? Right here, we can pick n big enough. So you can, first of all, this is PII, okay, one term, and the rest of term is k less than n, and k not equal to I. PIK. From here. So we single out this term, okay, and this is the rest. Okay, and for H, so the result is that so this one as H goes to 0, this is the finite sum, right? So this is go to QIK. Because that Chinese probability function is right derivative of time equal to 0. So this is equal to QIK, and this is PKJ. And if for this one, and by continuity, when H goes to 0, this is PKJT2. Okay? So there's no problem. And this one is mutual. Okay, and the term here. The limit, we have the sum. We have the summation here. So this is the upper bound. And then by n goes to, so this is true for all the n greater than I. Okay. Now, as n goes to infinity, the summation will be all the QIK and k not equal to I, and by the conservative property, this is cancelled, right? You can cancel that. So you can cancel them. Okay. So the summation. So when we cancel, compare them, then the lim sup has the upper bound, which is equal to the sum for all k. Yeah, because n goes to infinity. and k not equal to I. So this is the situation that the dim soup has this upper bound. Alright, and so the dim soup has upper bound and dim inf have the same lower bound here. We have the same lower bound. Alright, as n goes infinity, so lower bound is here. So dim inf has a lower bound, and the dim inf always less than or equal to dim soup. Alright, so that by sandwich property that they will be the same. Okay, and so we prove that that this limit exists and also equal to this dimension. So the breakwater equation is quite easy to prove. By using the limiting procedure. Okay. Alright, and there's a remark that the converse of the theorem. Oh, okay, yeah, I'll finish this. So the converse is also true if continuous time Markov chain has homologous backward equation. Then it is also conservative. So it's an only condition for the homologous backward. So this is if a continuous Markov chain with conservative chain input, we have the homologous backward equation. Conversely, if we have a homologous backward equation, we can prove that all the transition wave function are conservative. Okay, so I finish it. Let's stop here, and I'll see you next week.